going to exchange hydrogen ions, we wouldn't want the hydrogen attached to the fluoride ion, would we? Because not a lot of exchange would take place. If we want a spontaneous acid-base reaction, one where lots of hydrogen ions are transferred, then we're going to attach the hydrogen ion to the weaker base and let the stronger one take it away. Now, real quick, have I got a deal for you?
Yes.
These are ions, right? And as such should have aqueous symbols under them, right? These both have aqueous symbols under them. Actually, everything here is aqueous, right? Here's the thing. In this course, the only place we run into ions by themselves, independent ions, is when they're dissolved in water. Now, that's not true for neutral molecules. We find neutral molecules as gases, liquids, solids, as well as dissolved in water. But if we have ions in this course, they're always dissolved in water. So let's save ourselves a little time and trouble, shall we? Let's agree, you and me, that when we write equations that contain ions, that we'll leave off the aqueous symbol, and we'll agree that we all understand if you have an ion in an equation, how can you tell it's an ion? It's got a charge, right? If you've got an ion in an equation, then you assume that it is in aqueous solution. Now, will that work after you leave here? No. You can't, you don't want to embarrass yourself in your college chemistry class and go, oh no, you know, my chemistry teacher told me we don't have to write that, because this is just an agreement for you and I, and it lasts a total of, you know what, 9 weeks, 8 weeks, okay? And then the agreement is null and void. We okay? But it'll save you a little writing when you're writing equations. It'll save me a little writing as I'm writing equations on the board as well. Okay?
Why would the sulfate have 2 hydrogens?
Well, the question is, could this reaction, could we do this? And that's a spontaneous acid-base reaction. But it's a different acid-base reaction than this one.
I did that. But both of them work?
Well, one of them, this one involves a fluoride ion, but I don't see a sulfate ion anywhere.
Oh, because...
There's an SO4 in here, but there's not a sulfate ion acting as a base here. Or an acid for that matter. So this would not have been an appropriate answer for the question. Now, when we have an acid that has 2 hydrogens on it, by the way, we have a term for an acid that has 2 hydrogens on it. They're called diprotic acids. Oh, we always throw things out, every once in a while, even while we're answering homework questions. An acid that has 2 hydrogens is called a diprotic acid. Where does the word diprotic come from? Di means 2, protic refers to protons. That's right. Guess what an acid that has 3 hydrogen ions is called? A triprotic acid. Guess what an acid that has 1 hydrogen ion is called? Monoprotic acid. Now, typically, we don't use the term monoprotic. If I say HCl, is that an acid? You know, you wouldn't just go, no, it's a monoprotic acid. Okay, now, diprotic, monoprotic, triprotic refers to how many hydrogen ions are there. Okay, now, when you have a diprotic acid, it can lose 2 hydrogen ions, right? So here is a diprotic acid losing 1 hydrogen ion, and here is the diprotic acid losing its 2nd hydrogen ion. But we write the reactions typically separate from one another because they're 2 separate processes. They have 2 different extents to which they will occur. This will occur much more easily and is much more spontaneous than this one is. You might expect that acid that has 2 hydrogen ions would give up the first one easier than giving up the second one. Do I need to explain why that might be the case? We might expect that to be the case. Easier to get a hydrogen ion that's positive away from a neutral molecule than a hydrogen ion that's positive away from a negative ion. Does that make sense?
If it was a like CO3 instead of a chloride, would it you write it like the second way and have it take away the
Okay, now we are changing the question. Is that what you're talking about?
Instead of a fluoride, it was like
Oh.
CO3 and it can take two.
Again, one at a time, huh? Right? Because the first one leaves easier than the second one. Now, are both of these things happening in the solution? The answer is yes. If I put a solution of carbonate ions together with a solution of sulfuric acid, both of these things are taking place. We like to think of them separately because one occurs to a much greater extent than the other one does. But if I poured these two solutions together and they reached equilibrium, we would have some of this, and some of this, and some of this, and some of that, and some of that. All of those things would be present. We wouldn't have as many of these, however. We wouldn't have as many of these, and never mind. I was thinking I was going to make a point that would clarify things a little more, but I don't think it is.
So what is the equation?
Proving. Sam's point was, what if we start out with a base that could take two hydrogen ions? We had a fluoride ion here before, right? And it could only take one hydrogen ion. What if we have one that takes two? Can it take two? Well, yes, but we still like to think of them one at a time.
How do you know when to use the double arrow things?
All of our acid-base reactions are reversible reactions.
So only ever we write an equation to always include.
It's not especially important. I'm writing it to be proper and so that in some circumstances we can talk about, like the difference between a strong acid and a weak acid, why one will go to a greater extent than another. So when the equilibrium aspects of this are something we're focusing on, I'll emphasize that. But for you, it's not especially important for right now.
Could we have a reaction that goes equally quickly both directions?
Well, first of all, as you might suspect, when this reaction reaches equilibrium, the reactions are going in the opposite directions at the same rates. That's what equilibrium is all about, right? Equal rates of those two opposing processes. But probably what you meant to say was, can we have an equation that has an equal tendency to occur in each direction? And the answer is yes. If we had two bases competing for a hydrogen ion that were exactly the same strength, okay, correct. A was the only one of the three that was spontaneous. Careful on the test. If I give you a question like this, there may be more than one that's spontaneous. There may even be none that are spontaneous. It's going to be a mark all that apply thing. Thought.
Are there going to be any calculations this chapter?
Yes. Edge.
Oh.